Now in this lecture we shall learn about the section 2 of, we can say, AS 1170 part 0. That basically deals, or we can say it guides us regarding the structure design procedure. That is the procedure that we do need to follow when we are designing any kind of structure. So, when we are dealing with the design of the structures, we are basically dealing with the two types of requirements. One is, we can say, the ultimate limit state, and second is the serviceability limit state. So we can say that the ultimate limit state, that is the first, we can say, criteria, and second is the serviceability limit state. So how exactly are we, we shall discuss in detail what exactly we mean by the ultimate limit state and what exactly we mean by the serviceability limit state. So when we are dealing with the structures, we are right now, when we are dealing in with design a structure in 2023, we are dealing with two types of limit state, and we do need to have two kinds of check whenever we are designing the structure. One check is that when, let us suppose, we are designing this particular beam, which is basically simply supported on both the ends. Now when we are putting the load onto the top of, we can say, this particular beam, we do need to ensure that, in simple words, the stresses that are coming at, we can say, bottom of this particular steel beam, or the shear that is coming at the both the ends, that should be within the limit. So those stresses, or we can say shear or bending moment or torsion, or for these kind of structural checks, we do check that in the ultimate limit state with factored load combinations. So the load combination that shall be used for, we can say, design, that shall be factored load combinations, and that basically deals with, we can say, checks of the stresses, or we can say shear force, bending moments. So that is basically the, we can say, a simplified definition of the ultimate limit state, that when we are checking the stresses for the factored load combination, it should be within the limits. When we are dealing with the serviceability design, we do need to ensure that whatever loads are coming in that particular case, the deflection of this particular steel beam, let us say if we are having this particular steel beam, it shall bend something like this. So this deflection, that should be within the limit, and many times it do happens that if we go as high as the allowable stresses, but we do not check the, let us suppose, the deflection check, so in that case it might happen that the girder, or the steel beam, can deflect a lot, and that deflection shall have an impression that the steel beam has failed, but in reality the stresses are within the limits. So that is what the basic definition of serviceability limit state, that we do need to ensure that whatever this deflection or vibration, or we can say cracking checks, so those checks has to be within the limit, and that are not checked for the factored load combination, that are checked for the unfactored load combinations. So instead of adopting factor of 1, let us suppose 1.35 dead load plus 1.5 times live load, we do check for 1 times load combinations only. So whether we do need to check for dead load or live load, that shall be as per the design criteria set in the concrete or steel codes. So that is the, we can say, basic definition of ultimate limit state and serviceability limit state. So if we are talking about the concept wise ultimate limit state, so we can say that we have this limit state of we can say limit state of bending, we can have limit state of shear also, we can have limit state of torsion also. So these kind of limit state are basically categorized when we are dealing with the design. And when we are dealing with the serviceability limit state, we are dealing with the serviceability limit state of deflection. We are dealing with the serviceability limit state of, let us say, sway also on the top, that is if the building can usually get sway also in the case of the wind load. So this we can say lateral deflection or top or sway, that has to be within the limit. Or we can say serviceability limit state of vibration also. So all of these checks has to be done before we submit the drawings at the site for the construction. So when we're dealing with the structural design procedure for, we can say, Australia, so first of all, the first thing that needs to be checked is that we need to find out the importance factor. We do need to find out the importance factor. Now, in the consideration of importance factor, either we do need to refer to the NCC, that is the National Construction Code, when we are, we can say, dealing in buildings or structure in Australia. And when we are dealing with the New Zealand structures, we do need to refer to AS 1170 itself. We do need to refer to AS 1170 part 0 itself. So if that code is open in front of you, you do need to refer to the table 3.2, table 3.1 and table 3.3. So 3.1, 3.2 and 3.3, that basically deals with deciding or consideration of the return period for the appropriate importance factor. So we shall discuss this about this NCC also. Let me just show you the we can say the code considerations. So these are the consideration that is given in the NCC, that is National Construction Code of Australia. So this is given in National Construction Code, and this is given in the guideline of the National Construction Code. So if the building importance level is importance level 1, that can be assigned to building or structure presenting a low degree of hazard to life and other property. If if we have a building or structure that is not included in 1, 3 and 4, that has to be in importance level 2. If building or structure is designed to contain a large number of people, let us say 200 or 300 people can be inside the building at a time of earthquake or at a time of the extreme winds. So in that case, importance level has to be 3. And buildings or structure that are essential post disaster recovery or associated with hazardous facilities. Let us say we are talking about a dam, or we are talking about the the shelter in the cyclonic shelters. So in that case, we have to assign importance level 4 to those structures. And when we are dealing with the, we can say, design events or the importance level or the annual probability of exceedance, so here we can see that this is basically the annual probability of exceedance for non-cyclonic wind, annual probability of exceedance for cyclonic wind, annual probability of exceedance for snow, and annual probability of exceedance for the earthquake. So in short, we are dealing with the non-cyclonic case, cyclonic wind case, third snow, and fourth earthquake. So let us say the building that we are dealing with importance level 3 building. Let us say we are talking about a hospital or a medical emergency building. So in that case, if we are dealing with the non-cyclonic wind, we have to consider the return period of 1000 years. And annual probability of exceedance for cyclonic wind also for 1000 years. For snow, we have to consider 200 years. And for earthquake, we have to consider 1000 years. So that is the basic criteria to first of all how to decide the importance level, and then how to decide the return period, that is the annual probability of exceedance also. These are some of the examples when we're dealing with the importance level 1. So let us say we have to construct this particular, we can say, farm building and farm shed. So in that case, we can assign importance level 1. So that is the, we can say, least importance level given in the Australian standards. So we have to we can assign importance level 1 to these farm buildings and farm shed, or we can say isolated minor storage facilities or minor temporary facilities. So that is the first criteria. If we are dealing with the importance level 2 structures, importance level 2 criteria is that this is one of the example of importance level 2, that is low rise residential construction and building in facility below the limit set for the importance level 3. Now importance level 3 is the we can say most common when we are dealing with the structural design done in Australia. So most of the times when we are dealing with hospitals, or when we are dealing with the office buildings, or when we are dealing with college structural engineering of colleges, or when we are dealing with different kind of structures, usually we do encounter importance level 3. So buildings and facilities where more than 300 people can congregate in one area. Building and facilities with a primary school, secondary school, or daycare facility with a capacity greater than 250. Now, does it mean that, let us say, if the capacity of the primary school is less than 250, can we assign it to importance level 2? Now, that is like a decision that can be taken by a structural engineer. Now, if I am the structural engineer, I shall always go ahead with the importance level 3, considering that schools are a structure that should remain intact in the case of extreme events or in the case of an extreme earthquake. We cannot risk the life of the children, even if the code is not saying you to do that. So that is why, if I am the engineer, I shall always go ahead with the importance level 3 when we are dealing with the primary school or secondary school, even if the capacity is less than 250. That is my point of view. After that, buildings and facilities with a capacity greater than 500. Let us say we are talking about colleges or adult education facilities, or healthcare facilities with a capacity of more than 50. And jails and detention facilities, any occupancy with an occupant load greater than 5,000. Power generation facilities, water treatment and wastewater treatment facilities, and building facilities not included in importance level 4, containing hazardous materials capable of causing hazardous conditions. So let us say when we are dealing with the industrial structures, or structures which are storing, we can say, harmful chemicals such as sulfuric acid, or we can say very highly hazardous alkaline or hazardous acidic chemicals. So in that case also, we should always go ahead with minimum importance level 3 load guidelines. After that, when we're dealing with the importance level 4, now building and facilities designed as essential facilities, building and facility with special post-disaster functions, medical emergency or surgery facilities. So in here, if we can say, if the healthcare facilities with a capacity of 50 or more residents but not having surgery or emergency treatment facilities, in that case it lies in the importance level 3. But if the hospital, usually it has surgical facilities, so in that case we have to assign importance level 4. And after that, emergency service facilities such as fire, rescue, police station, and emergency vehicle garages. And utility required as backup for the building and facilities for importance level 4. So let us say we have to make a utility building for, we can say, surgical, or we can say hospital having surgical facilities. So in that case also, the supporting building shall also be importance level 4. And designated emergency shelters, or we can say emergency central and ancillary facilities, or building and facilities containing hazardous chemical capable of causing hazardous conditions that extend beyond the property boundaries. So usually, when we're dealing with the industrial projects, dike wall, or we can say bund wall, is made whenever we store harmful chemicals. So let us say this is the tank in which we are storing hazardous chemical, let us say HCl. So in that case, hydrochloric acid. So in that case, even if the acid spills, the bund wall is designed such that this chemical remains inside. This chemical, that shall not flow, or we can say outside this particular bund wall. So this bund wall is designed such that whatever pressure is coming from the, we can say, the pressure from this liquid, it can sustain it. So that is a basic criteria. So that is why, when we're dealing with the industrial structures, there is a separate code also which guides us regarding how we can, design the height or the storage capacity of this bund wall. So that also we shall discuss. But, just to give you a brief idea here, if we are dealing with industrial structures, we are dealing with the importance level 3. But when we're dealing with this kind of, we can say, emergency buildings or medical or emergency facilities or surgical facilities, in that case, we have to deal with the importance level 4. And under the importance level 4, we are dealing with a case where we are targeting return period of 2000 years, and when for earthquake we are targeting return period of 1500 years. So that is, I can say, at par with what other countries are considering. It is not like that we are going on a very conservative side. this we can say for earthquake 1500 return period and for cyclonic wind 2000 year return period. That is at par with what other countries are considering, or we can say it is a little bit lesser itself. It is not on the higher side. So that is, I repeat my point of view here. So this, we have discussed uh, for Australia itself. So this text or the snapshot that we have considered on the top, that is from basically NCC, that is National Construction Code. I think that was released latest in the year 2019. So that was just an introduction of how we can, classify the importance level of the structure. And as per the, we can say, importance level, accordingly, we can decide the annual probability of exceedance. After that, when we are dealing with the New Zealand as a country, we do need to refer to the table 3.1 that is given, and we can say table 3.2. So more or less, the clauses or the pictures given are same, but that we shall discuss very shortly in the next lecture. So in this lecture, I shall restrict my discussion to the consideration of the importance level for Australia and the guidelines set in the NCC, and accordingly, I shall explain you regarding the brief introduction to the ultimate limit state and serviceability limit state. So we have, the first step that we were dealing with the ultimate limit state was that we have to, design, or we have to decide the importance level. So that can be done as per the, we can say, NCC, and accordingly, we can decide the importance level, and accordingly we can decide the annual probability of exceedance or return period also. So after that, the second step shall be that we have to, we can say, decide the permanent action is denoted as G, and imposed load or imposed action, that is classified as, we can say, Q. And after that, we have to, decide the, we can say, ultimate load for wind also. So after that, we have to calculate the wind load. So wind load can also be determined as per the return period. And after that, we have to determine the ultimate load for earthquake also. So ultimate load for earthquake, that we can, classify as EU. So that we can say that shall be for, we can say, Australia, and the code that help us in calculating the Australian earthquake load, that is basically the AS 1170 part 4. So accordingly, after that, if the building that is, we are categorizing, that is in an area where there may be snow also. So after that, we have to determine the snow load also. So snow loads that can be categorized as, we can say, FSN, or we can say ice loads also. So let us say we are dealing with the transmission tower. In that case, the ice load also needs to be considered, because the ice can get, we can say, frozen on the wires also, or on the transmission cables. So after that, we have to deal with the other pressures, we can say, such as if the water tank is coming, we have to deal with the this liquid pressure, or we have to deal with the earth pressure if the retaining wall is coming. So after that, when all the actions have been finalized, at the end, we do need to determine the combination of actions also, or we can say load combinations. So when we are dealing with the combination of actions, again the AS 1170 itself guides us that how we can calculate the combination of actions as per section 4. So section 4 deals with basically the load combination, or in the code language deals with the combination of actions. So let us say, when we are dealing with the this particular load combination, one of the load combination that we are dealing with 1.35 G, that is 1.35 times the self weight. After that, when we're dealing with the permanent and imposed action, the second load combination that we are dealing with 1.2 times G, that is dead load or permanent action, plus 1.5 times Q, that is imposed action. The next load combination can be that 1.2 times the self weight, plus we can say wind, plus we can say phi c times q. That is the phi c can be calculated, and q is basically the imposed action. Similarly, there are other actions also. That is, we do need to combine the permanent earthquake and imposed action. Like we have classified the permanent wind and imposed action here. Similarly, we do need to combine the permanent action, and we can say the imposed action, or we can say snow load action also. So all of these combinations are basically categorized as, we can say, in the strength combination also, or we can say stability combination also, or serviceability combination also. So all these actions, that we shall discuss in detail in section 4. But just to categorize here, that we have to, after calculating all type of loads above, that is, first action shall be the calculation of importance level. After that, we can calculate permanent and imposed load, wind load, earthquake load, snow load, and ice load if that is applicable. The liquid pressure load, or soil or earth pressure load. And after that, we have to combine these actions as per the load combinations that are given in section 4 of AS 1170.0 itself. So after that, we can analyze the structure. Now we can simply analyze the, we can say, structure with the help of either software or manual calculations also. Now I can say that, the software that is mostly used in Australia, most of the times it is space gas itself, or it is strand 7 for the, we can say, FEM analysis, or in some of the companies are using ETABS also, or we can say SAP 2000, or for calculation many of the companies are using ANRCalcs also. So these are the softwares that are using that are used by the engineers in Australia, so that we can refer to, and accordingly we can analyze and design the structure. Now when we have analyzed the structure and its components, after that we have to do the structural designing. So design and detailing. Now detailing part is very important when we are dealing with the buildings in high seismic zones, or when we are dealing with New Zealand as a country. So in New Zealand, basically because of the high, or we can say high intensity earthquake, we do need to ensure that ductility of the structure, or we can say ductile detailing. So that has to be done as per the code itself, so that the appropriate hinge formations shall be there in the case of an extreme earthquake and structural does not fail. So hinge formation is basically a process, where let us say this is the portal, and these are the columns, and this is the beam. So these are the 3 columns, this is the beam. So when horizontal earthquake action strikes, basically there is this, we can say, hinge formation at the ends of the structure. So this hinge formation, we can say that at this particular point, we can say it behaves something like this. So this whole action, we can say, it fails from this particular point rather than failing at the center. And how we ensure that? We ensure by providing a very closely spaced ring here, and in the center area the rings are not that much closely spaced. So due to the concentration of closely spaced rings, the hinge formation is concentrated in that particular area itself. Similarly, for columns also, hinge formation is there in this particular junction, and the rings are widely spaced, and again at the supporting point the rings are again closely spaced. So all of these, that is a part of ductile detailing itself. So that ensures that structure, although they are always designed for, we can say, no collapse. So it is the the standard philosophy of all the country codes that in the case of an extreme earthquake, or in the case of an extreme wind or extreme cyclonic wind, even if a structure shall deform, or there may be hinge formation, but it should not collapse. So that is why, that is the philosophy, that structure should not collapse in the case of an extreme event, and that is a basic philosophy. However, as per nowadays, when we are dealing with a performance based design also, so in performance based design, of structures, we can skip this part and we can, there are these other categories also when we're dealing with the performance based design. That is, we deal with the IO, LS, and CP stage. IO is basically immediate occupancy. That is, even after an extreme earthquake or extreme cyclonic wind, there is no as such damage to the structure and the structure can be immediately occupied. Second one is life safety. That is, a structure may experience minor, we can say, hinge formation or minor, extreme event, but again, all the life or the occupants that are inside the building, they shall be safe. Collapse prevention is that the building or structure may become unusable after the extreme event. We may have to dismantle the complete structure, but at the same time, the structure shall not collapse, and we can say the occupants are also safe inside that particular design building. So that is basically, we can say, collapse prevention. So these three are the, we can say, stages, or we can say part of the performance based design. So this performance based design philosophy is more prevalent when we are dealing with the high seismic zones such as California, or we can say in European continent also. This philosophy is now getting its hold and is now much more commonly used. But in Australia, when we're dealing with this wind as a major governing load and earthquake not as a major governing load, that is not a part. And in New Zealand, when we're dealing with design, most of the buildings are now base isolated. So what they have done is that in New Zealand, in most of the buildings, they have done the base isolation, just ensuring that the structure shall not collapse or experience a severe, we can say, cracking or experience a severe deformation in the case of an extreme earthquake. So that is a philosophy that in New Zealand they have adopted, and that is also much more commonly used in New Zealand because much of the research work for base isolators that have been done in New Zealand itself in contrast to the other countries. So that is why in New Zealand most of the buildings are now older buildings that have been constructed like 50 to 60 years back. They are also getting base isolated. So after that, we can confirm that in the next stage, the last stage shall be that we can confirm that design resistance, or we can say the structure that we have designed exceeds the loading actions or the combination loading action that shall come on the structure. So all this that we have studied on the top, that forms the part of the, we can say, ultimate limit state. So this forms all of these points that we have discussed, they all form the part of the ultimate limit state. But when we are dealing with the, we can say, serviceability limit state, we do need to do the same process. We do need to design the structure, but the only difference is that instead of the actions that we have taken as 1.35 g or 1.2 times g plus 1.5 times q, we have to go for the serviceability load combinations. So we have to repeat the same process except for the combination of actions. In combination of actions, the load combinations, or we can say the combination of action, that is different when we are dealing with the limit state of serviceability. And in addition to that, when we are dealing with the limit state of serviceability, we do need to also ensure that the serviceability response of the structure and its part for the relevant combinations, that should also be within the limit. And similarly, when we're dealing with the New Zealand as a country, we do need to ensure the serviceability limit applicable to the earthquake loading, that should also conform to the NZS AS1170 part 5. So this code has basically guidelines on what exactly can be the maximum, we can say, interstory drift. That is, the interstory drift is basically the drift of a particular story, or we can say what exactly can be the maximum lateral deflection in the case of an earthquake, or we can say what exactly can be the relevant seismic action check, such as the beam column capacity ratio, that is BCCR, And there are other, a long list of checks that is given in the AS1170 Part 5 when we're dealing with the earthquake actions in New Zealand. So that is basically a brief introduction to the, we can say, ultimate limit state, or limit state of strength, we can say, or and limit state of serviceability. So basically we have right now, studied only page number 10 and 11 of AS1170 Part 0. So that basically deals with the both of these, that is the limit state of ultimate limit state and serviceability limit state.